Welcome to today's episode. We're exploring the distinctions between AI agents and agentic AI, guided by the recent paper titled AI Agents versus Agentic AI, a Conceptual Taxonomy, Applications and Challenge by Ranjan Sapkota, Konstantinos I, Roumeliotis, and Manoj Karkee, published on May 15, 2025. This study offers a structured taxonomy differentiating modular AI systems powered by large language models from more advanced, collaborative, and autonomous agentic architectures. It delves into their architectural evolution, operational mechanisms, and levels of autonomy, highlighting the limitations of current AI agents and the amplified challenges introduced by agentic AI. The paper also proposes potential solutions and a future roadmap for development. The paper reminds us that the idea of autonomous agents isn't entirely new. It has roots in older fields like multi-agent systems, often called MAS, and even expert systems. Foundational work, like that by Castelfranchi on how individual actions lead to social behavior, or Ferber's frameworks for multi-agent systems, thought about concepts like autonomy, perception, and communication a while back. But the paper draws a clear line between those older systems. Think expert systems like MYSN, early robotics like the Stanford cart, or even AI in old video games, and the AI agents we talk about now. The key difference highlighted is that older systems were very much rule-based. They followed scripts and couldn't adapt much beyond their programming. Today's agents, according to the paper, are much more driven by learning from data, understanding context better, and adapting more dynamically. It's a big shift from just following rigid rules. The paper presents data, like Google Trends shown here in Figure 1, indicating a significant rise in interest for both AI agents and agentic AI starting around late 2022. This coincides with when large generative models really took off, what the paper calls the ChatGPT era. This rise wasn't just hype. The data suggests a real change in how people saw AI's potential, moving towards actively trying to build and use these more autonomous systems. The paper traces this evolution post-ChatGPT. First came the popularity of generative agents, systems based on large models designed to create content like text, images, or code from prompts. Examples include early GitHub Copilot or Jasper. Building on this, AI agents emerged, and finally, the more complex agentic AI. So, let's get to the fundamental difference the paper emphasizes: AI agent versus agentic AI. At its simplest, the paper defines an AI agent as typically a single system focused on a specific, well-defined task. Think of it like a specialized tool. One agent, one primary job. In contrast, the paper explains that agentic AI involves multiple agents working together, coordinating to handle broader, more complex workflows, things a single agent alone couldn't manage. It's like a team versus an individual. The paper stresses that making this distinction clear, having a proper taxonomy, is scientifically important. It helps in designing systems better, knowing if you need a single agent or a team, and in benchmarking how you test them. It helps avoid confusion and wasted effort by using the right approach for the right problem. Let's dig deeper into AI agents, according to the paper. They are described as autonomous software entities for goal-directed tasks within bounded digital environments. The paper highlights key characteristics, shown here, referencing Figure 4. Autonomy: they can act independently once set up, minimizing human intervention. Task specificity: they are built for narrow, defined jobs like scheduling or filtering data. Reactivity and adaptation: they can respond to changes in their environment and sometimes learn from feedback. The paper stresses the crucial role of large foundational models, LLMs, or large language models, like GPT-4, and LIMs, or large image models. LLMs provide the reasoning power and language understanding. LIMs bring the visual side, letting agents understand images. Figure 5 in the paper shows an example: a drone inspecting fruit in an orchard using image recognition. Access to these models through APIs and frameworks like LangChain or AutoGen has made building these agents much easier. As a reminder, the paper positioned basic generative AI as a precursor. Its key limitations were its reactivity, only responding to prompts, being stateless, not remembering context, and needing external wrappers to interact with tools. It creates content well but isn't a proactive problem solver. These limitations led to the development of more capable AI agents. They build on LLMs' language skills but add memory, planning, and crucially, the ability to use external tools. The paper calls LLMs the engine for this progression. Frameworks like React formalize this. The agent reasons, then acts, maybe by calling a tool, then observes the result, and uses that observation to inform the next reasoning cycle. This is more dynamic. Examples given include AutoGPT for market analysis or GPT Engineer for coding. Figure 6 shows a news query agent workflow combining reasoning and external search. Now, Agentic AI. The paper says this emerged to tackle the limitations of single AI agents, especially with complex, multi-step tasks needing different kinds of expertise. It's a conceptual leap, moving from one agent doing its job to a system of agents collaborating towards a higher-level goal. Multiple specialized agents work together. They coordinate either through a central orchestrator or more directly among themselves using things like shared memory. Key enablers mentioned are breaking down goals into smaller tasks, multi-step reasoning, communication between agents, and reflective reasoning. These capabilities allow tackling much bigger, more intricate challenges. The paper uses the smart thermostat versus smart home analogy, Figure 7. The thermostat is like the single AI agent, specific task, operates in isolation. The smart home ecosystem, with multiple specialized agents, weather, schedule, energy, security, interacting synergistically, is like Agentic AI. They communicate, share memory, and collaboratively optimize towards a high-level goal, like comfort and efficiency. Architecturally, Figure 8, Agentic AI builds on the basic AI agent structure, perception, reasoning, action, but adds layers. An ensemble of specialized agents instead of one. Advanced reasoning and planning techniques like chain of thought or tree of thoughts. Persistent memory architectures. Crucially, an orchestration layer or meta-agent that manages interactions. Think of ChatDev's virtual CEO role. So it's not just more agents, it's a more sophisticated structure for managing them. Where does the paper say we're seeing these systems used? Figure 9 gives an overview. For AI agents, it's often automating specific, defined functions, Figure 10. Customer support and internal enterprise search, like parts of Salesforce Einstein or Intercom Fin. Email filtering and prioritization. Personalized content recommendation, Amazon, Spotify, and basic data reporting, Tableau Pulse, Power BI Copilot. Autonomous scheduling assistants, X.AI, Reclaim AI. These mostly focus on handling defined, often repetitive tasks efficiently. Agentic AI applications are geared towards more complex, collaborative tasks, Figure 11. Multi-agent research assistants using frameworks like AutoGen or Crew AI for complex tasks like drafting grant proposals, Figure 11a. Intelligent robotics coordination, like multiple drones or robots working together in farming or warehouses, e.g., Apple Orchard Harvest, Figure 11b. Collaborative medical decision support in hospitals, ICU example, Figure 11c. Adaptive workflow automation for complex processes like cybersecurity incident response, Figure 11d. These examples rely heavily on that collaborative, multifaceted problem-solving capability. It's not all smooth sailing, and the paper dedicates a good portion to challenges and limitations, Figure 12. For single AI agents, the paper flags issues, Figure 12a. A lack of real causal understanding. They are good at correlation, not always cause and effect. They inherit limitations from LLMs, like hallucinations, making things up, biases, and they can be sensitive to prompt wording. Sometimes they have incomplete agentic properties, meaning they aren't fully autonomous or proactive. They can struggle with long-horizon planning and error recovery. There are still reliability and safety concerns, especially for critical tasks. For Agentic AI, these problems often get amplified, and new ones emerge, Figure 12b. Amplified causality challenges due to complex interactions. Communication and coordination bottlenecks between agents. Emergent behavior and unpredictability. Unintended consequences can arise. Scalability and debugging are harder because it's like multiple black boxes interacting. Trust, explainability, and verification become even bigger issues. Security and adversarial risks increase. Ethical and governance challenges get more complex with multiple agents. The paper states the foundations are still immature, with research gaps and a lack of standard architectures. It sounds daunting, but the paper also offers potential solutions and a roadmap forward. Figures 13 and 14. Figure 13 outlines about 10 emerging solutions, things like retrieval-augmented generation, RAG, to make outputs more factual, using tools more effectively via function calling, improving the agentic loop, reason, act, observe, better memory architectures, specializing roles for agents and orchestration. Other solutions include adding self-critique mechanisms, better programmatic prompt engineering, using causal modeling for planning, and building in monitoring, auditing, and explainability from the start. Finally, governance-aware architectures are needed for accountability and ethical reasons. Figure 14 sketches out the future roadmap. For AI agents, it points towards them becoming more proactive, better integrated with tools, developing causal reasoning, learning continuously, and becoming safer. For Agentic AI, the roadmap emphasizes scaling multi-agent systems, better unified orchestration, shared persistent memory, using simulations for planning, establishing ethical governance, and creating domain-specific systems tailored for particular industries. So, wrapping up our look at this paper, the core distinction is key. AI agents are typically single entities for specific tasks. Agentic AI is about multiple agents collaborating on broader goals. We've traced the evolution from foundational AI, through generative AI, to AI agents, and now these emerging agentic AI systems. Both hold huge potential across many areas the paper touched on. But, as the paper makes very clear, there are significant hurdles still to overcome in areas like reliability, coordination, safety, and explainability before that potential is fully realized. This research gives us a solid framework for understanding the landscape. Thinking about the challenges and the roadmap the paper laid out, it leaves us pondering, what breakthroughs are truly needed to unlock the next level of AI capability discussed in this research? Thanks for joining this deep dive. For the full paper, check the description. See you in the next paper.